Most of the complicated finance decisions involve cash flows that stretch out longer than a year. Therefore, we need to consider the time value of money. Cash flow timing has important economic consequences. The time value of money is based on the belief that a dollar today is worth more than a dollar that will be received at some future date. What would you rather have, money now or money later? Present money is worth more than future money. We are not referring to the purchasing power of the same money, that is inflation. Rather, we are talking about the alternative use of money, also referred to as the opportunity value of money. That is, the value that comes from the different opportunities today on using the money, rather than waiting for it in some future date. So when cash flows extend beyond one time period, consider the time value of money. To repeat, cash flow timing has important economic consequences. Time value is based on the belief that a dollar today is worth more than a dollar that will be received at some future date. Simply stated, the focus is on the value of money now versus money later. Interest is the return received for investing money for a period of time. Compound interest is the interest that your investment earns on the interest that your investment earned previously. The great scientist Albert Einstein said that the most powerful force in the universe is compound interest. Calculating the time value of money involves a variation of one formula that is used to solve for which of the following four factors is unknown: the future value, as in the future results that come from compound interest, as Albert Einstein was referring to; the present value, where you know the future cash flows, but not the current value; the interest rate, or the compounding rate that is used in either the future value or present value calculations; and the time periods of the cash flows. In this module, we will only solve for the future value or the present value. We put aside the algebraic derivations to solve for an unknown interest rate or time periods. Throughout this module, we will be using dollars for the monetary unit, but of course it works for any monetary unit. We can take a simple 2-year example to show the way the calculations work. Assume the present value, or PV, is $100 of principal today. Assume further that you can earn 10% annual interest on the amount of principal invested. By the end of the first year, you would earn 10% times your initial $100, or $10. Not showing here, but at the end of 1 year, your account would consist of the initial $100 and the interest earnings of $10, totaling $110. But we want to go on 1 more year. In that second year, you can earn the same 10% annual interest on your initial $100 of principal, thus earning another $10. But in addition, you can earn 10% on the $10 of interest earned in the first year, which computes to $1 of interest. Therefore, the future value, or FV, of having $100 to earn interest compounded annually for 2 years amounts to $121. This example shows the 4 factors. Present value is $100. The future value is $121. The compounding rate is 10%. And the number of compounding time periods is 2 years. Now we will start a series of slides to show how to solve for a missing future value or present value. We first show how to solve for the missing future value. Suppose you have $2,500 today, which is the present value. You can invest that amount in a 3-year bank certificate of deposit, or CD, yielding 5% compounded annually. How much money would you have when this financial instrument matures? Thus, you are solving for the missing future value. After 1 year, your bank certificate of deposit is worth the initial present value of $2,500 times the product of 1 plus the rate of 5%. The result is $2,625. After 2 years, the CD is worth that $2,625 times the product of 1 plus 5%, or $2,756.25. A shortcut to avoid the prior steps is to compute it this way. The initial present value of $2,500 times the product of 1 plus 5% raised to the power of 2. The exponential number 2 is the number of annual time periods that the initial money is compounded. After 3 years, the CD is worth that $2,756.25 times the product of 1 plus 5%, or $2,894.06. A shortcut to avoid the prior steps is to compute it this way. The initial present value of $2,500 times the product of 1 plus 5% raised to the power of 3. The exponential number 3 is the total number of annual time periods that the initial money is compounded. What all of this means is that $2,500 today is worth $2,894.06 at the end of 3 years at an annual compound interest rate of 5%. More generally, then, the formula for solving for the future value is stated as: the future value is equal to the present value, or initial lump sum, times the product of 1 plus the annual interest rate, raised to the power of the number of annual time periods that interest compounds. A good way of understanding this process is through the use of a timeline. We draw the timeline with the number of years noted, from 0, which is the present, 1, which is the end of 1 year, and so on. We add in the interest rate, in this case 5%. We show the present value, or PV, at time period 0 as a negative. Why? Most business calculators and computer spreadsheets, such as Microsoft Excel, are built using a business perspective. Firms make an investment in the present by buying another firm, building a new manufacturing facility, hiring new staff, buying back their shares of ownership being traded on the open market, or any number of other, quote, investments. All of these choices constitute money out the door, or an investment, thus a negative number. Any cash flow thereafter is a return on that initial investment, and hopefully a positive number. Solving for future value is the initial $2,500 times the product of 1 plus the rate of 5% raised to the power of 3. So the result is $2,894.06. Until you are very comfortable with all of the calculations, I recommend drawing the timeline and the factors you know to visualize the problem being solved. How much would this bank certificate of deposit be worth at maturity if interest compounds quarterly? The trick is to convert the annual interest rate into a periodic rate and compound each period rather than annually. The formula then becomes future value is equal to the present value times the product of 1 plus the result of the annual rate divided by the number of periods per year, or I divided by M, raised to the power of the number of years times the number of compounding periods per year, or N times M. The M could be hourly, daily, weekly, monthly, quarterly, or any other compounding periods per year. Here it is quarterly, or 4 compounding periods per year. Plugging our previous example into this formula, but with quarterly compounding, produces the following. The future value is equal to the present value of $2,500 times the product of 1 plus the result of the 5% annual rate divided by 4 quarters, raised to the power of 3 years, times 4 quarters per year. Doing this, we get $2,901.89. Recall that with the annual compounding, you would have $2,894.06 at the end. With quarterly compounding, you would have $2,901.89 at the end of 3 years. This comparison confirms that the more compounding periods per year, the more interest you would have at the end.